Okay. Okay. Let me introduce Professor Jilin Hu, and I'm Bingo. I'm assistant professor from machine learning department. Jilin Hu received the PhD degree from Aalborg University, Denmark in 2019. He is currently an assistant professor at Aalborg University, Denmark. He has published several papers in EGK, PVLDB, ICD, TKD, and so on. And his research interests include spatial-temporal data management, traffic data analysis, analytic, and machine learning. He was a session chair for PVLDB 2020. He has been reviewed for several top-tier journals like IEEE TK, DVLDB journal, IEEE TNLS, neurocomputing, and he was also PC member for CVPR, AAAI, and AP Web 2020. Thank you. Welcome, Jilin, for the talk. So next is for you.
Okay, thank you, Professor Gu, for your introduction, and thanks everyone for coming for today's talk. And good afternoon. My name is Jilin. I'm from Department of Computer Science, Aalborg University, and the topic today that I shouldn't share my slides. No, it's okay. Now can you see my slides, right?
Yes, we can see.
Yes, okay. So my name is Jilin. I'm from Department of Computer Science, Aalborg University. And the topic today that is managing and analyzing big traffic data, which is an uncertain time series approach. So yes, this is the agenda for today, which we have several topics. First is introduction, and then we will come to this stochastic weight completion. And third is the stochastic origin destination matrix forecasting. And then we come to this latest work, which is about unsupervised path representation learning. And finally, we will come a conclusions and the future work. Yes, so introduction. So today the topic is about the traffic. So why do we need to study the traffic? Because the traffic is induced some problems, which can be this decreased air quality. Also, it can have some greenhouse gas emissions, and also it has some congestions which may be encountered. And there's a static that in 2014, around 370 US urban regions, which have a congestion hour, a total of 6.9 billion hours. And if we convert this into a how much money we cost on the congestion, it's around 190 billion US dollars. So that's a huge amount of money that's spent in these congestions. And if we can do something to improve the traffic and we can reduce these problems, it will be very good. So how can we do? What's the foundation that we can have for the data? So it's about the bigger traffic data. We talk about big data, and in the traffic domain, we have this big traffic data. So where is the traffic data come from? It can come from the vehicles. We have the GPS devices. So it has some emissions for the data, that's for the floating cars. And also we have some cameras on the road, so that this can record how many cars on the road or what's the speed like this. So we have the cameras, and also we have the loop detectors. And this is all the technique which is installed on some main road like highway or some freeways. So for this loop detector, they can once the car is passing by on the loop detector, it will have some data for the systems. So these are some devices. So when the vehicle is moving, then once the vehicle is moving, then they can have some GPS, right? Also the camera can have this one, and also if this car is passing by this loop detector, it will also have some data comes out. So this is where the data comes out. Yes. So what is the we have the data. So what is the characteristics for the traffic data. Then we conclude like this. We concluded it has three characteristics. First one, it's the spatial-temporal correlations, and also it has some sparseness. And then it comes to uncertainty. So finally, we come to our target, which is uncertain time series. And I will introduce that why we have this characteristics later on. Yes, so first, spatial-temporal correlations. What is the spatial-temporal correlations? Because for the spatial correlation, for a road network, we can model it as a graph, direct graph, right? For the node, it means the intersections on the road, and the edge, it's a road segments. For example, it's from one intersection to another one, we have an edge. So we can model it as a graph, a direct graph. So this one we can consider about the spatial correlations, right? And what is temporal dynamics? For example, that we take this E5 example here. So at different times, the traffic condition is different. Here we are using example of travel time as to show that how the temporal dynamic is. So it means that on this axis, it's the departure time on when the car is moving on this segment. So we can see that from 8 to 8:15, maybe it's in the morning peak, right? So that we can see that travel time, which is have 0.1 probability from 15 to 25 seconds. And maybe for 25 to 35 seconds, it has probability for 0.4, and for 35 to 45, it's around 0.5. So this is the travel time on this segment from this at this segment time at this time interval. And maybe later on that from 8:15 to 8:30, the traffic condition will be it's better because this one people are going to the office, right? So now the traffic it's better, so that it can travel much faster, which means that from 15 to 25, it's increased to 0.5 probability, and also 25 to 35, and it's 0.4, and then 35 to 45, it's 0.1. So this is also it's a change better. And then when we move on from 8:30 to 8:45, the traffic condition may be even better. So the traffic condition is different from time to time, which is temporal dynamics. That's why we call it spatial temporal correlations. Yes. So another characteristics about this data sparseness that people may question that. Okay, you mentioned that it's already in a big traffic data scenario. Why it still have some sparseness happen? Because for the road that first of all, we cannot get all the data on the road, right? For example, for the GPS data, maybe we can get some data from the vehicle which install some apps, or it's like the car hailing company like DD or Uber, they can have some data on the taxis. But for other vehicles, we cannot get the data. So it will have some sparseness in this situation. And also that there are some segments, maybe they have no data. So in this case that for E1, E2, for example, we have E1, E2, E4, and maybe for E1, they have data on this at these two time intervals. And E2, they may have data at this time intervals. And if E4 only have data on this time intervals. So they may miss data for 8:15 to 8:30, and maybe miss data from 8 to 8:15, and like this. So it means that if we split the traffic condition into a time fine granularity, which means that the time interval is very, very small, then the data sparseness will be very severe. So we need to address these problems, right? So next we will consider that why do we need to think about uncertainty? So that this is two paths, for example. Then this is start from the same edge, which is E5, and going to E1, and then going to E3. And this is a path which is still going from E5, and then it can go to E2, E4, and then go to E3. So this is two paths which have the same source and the same destinations, but the traffic condition is maybe different. For example, this path P1 from at 8:15 to 8:30, it may 0.3 probability which fall into 40 to 50, and 0.7 which from 50 to 60, and 6 to 70 the probability is 0. And then for P2, it may have 0.6 probability fall into this range, and 0.3 probability fall into this range. And also they have 0.1 probability fall into the 60 to 70 range. So what does this mean? So if normally that if we just give the user a pass, that we may just calculate the expected values for the travel time, right? So for P1, it has 52 minutes that is going to arrive with this pass, and P2, the expected value is 50 minutes. So in this case, that we will recommend is P2 to the user or to the driver, right? But what may be the problem here? So the problem is that if the driver want to arrive at the destination within 60 minutes, so we can see that P2 cannot guarantee the user to arrive at 60 minutes. That's why that we need to consider about this uncertainty to model it like a histogram or distribution. Then we can know better about the travel situations and can provide a better solution to the drivers. Yes. Okay, so this is the background, our introduction. Then we come to this stochastic weight completion. So let's look at what is stochastic completion. Actually, we have mentioned a little bit that, for example, we have a directed neural network, and this looks like this, which at one segment, maybe they have the travel time distribution on E5 and on E6, and then for E1 to E4, all these edges, they have no data, which means that maybe we cannot collect it or something else happen here. So if the edges is missing the weights, then we cannot do the routing, right? Because we cannot provide a good weight for the edges. So in this case, that we need to fill in which is the missing values here. So this is the initial representation for this road network, and which has 4 missing values for the 4 edges. And our problem is that how about that we can complete these missing values with some meaningful values in some models? Yeah, so this is a simple scenario that we can consider, and then we think about this. So we propose a model to learn to fill in these missing values. So the model currently it looks very simple, that we are using a autoencoder thing, and we adopt this graph convolutional neural network. So this is our framework, which it's very simple and generic graph convolutional autoencoder network, which means that we input as a adjacent matrix, and we also input the initial stochastic weight W. So this adjacent matrix it's derived from the road network, and then we take it into input, take it as input. Then we get this from graph convolution. We can do 1 layer or 2 layer. Then we can extract a high level graph node representations. And afterwards, that we do some clustering, because they have some missing values in E1 to E4 here, right? For example, then we can do some clusterings so that we can get more condense this feature with E5 and E6 here. And afterwards, we just do a fully connect to project them back to E1 to E6. And in this way, that we can let this model to learn the relationship between how E1 is related to this latent values, latent space, right? And E2 what's the relationship between these latent spaces, and then we can apply this softmax onto each vectors, because we want a stochastic weight, which means that it's kind of like the distributions. So we are using histogram to represent it. So for each vector, we apply a softmax to make it meaningful histograms. So this is our completed weights, which is simple. And then we propose an advanced one, which we consider more vectors. Here that we don't consider too much about the which time it is in and which day a week and which row this data is missing. So here that we consider a little more complex model, which is named context-aware GCWC, which means we consider this time interval, which what time it is on this day, and if we split 15 minutes as one time interval, so that in total that we will have a 96 time intervals in one day, right? And then for the day a week, that we can see that whether it's Monday, Tuesday, or it's weekends. And for rows flags, it's just to show that which row they have data or not. Then for this time interval, we can using an embedding layer, and here also we can using an embedding layer. And for this one, we just using a fully connected layer to do it. And then we try to see that okay, maybe they can learn a prior probability for this time interval, and this is prior probability for this day week, and this is prior probability for this row flags. And then we combine this one, which learned from this base model, and we can combine them with this CPCN, this model. And then we can do a Bayesian inference or something. We can just, if this is a conditional distribution, then we can multiply this one and get this conditional probability for this final predictions for the stochastic weights. So this is something we come up after that we propose of simple or base models. Yeah. And this is for weight stochastic weight completions. And next that because we still have this spatial temporal correlations, so we didn't consider this too much. And then we want to consider this, how can we use these characteristics? So here's our application or our motivation is from how about we do some original and destination metrics forecastings. So here is another concept we need to explain a little bit. So this one is that, for example, that we have a map, and we can split the map into different regions according to this main road, right? We can, according to this road, we can make it as one region, and this one also separated by the main road when we can make a second region. And this is there's also a river here, so we make them at different regions. So for this one, that we can split this, for example, this small area into eight regions. Oh, this one here is 8 regions, yes. And this is for the road-based partitions. And what if that's a user which is in region 6 and he or she want to go to region 3? Then he wonder that, okay, what's the probability that how much time I need to travel from this region to this region, right? So and also some user may be interested in how about this? I want to travel from 2 to 8, right? Also, what's the travel time? What's the probability for this one? So that we can construct this kind of like the OD matrix, which the row, this row is or for each column, for each row for each column it's represented the original, and for this one it's for each row it's kind of like the destination. So that for each cell, for example, if we want to 6 to 3, so we can find this. We start from 6 and we go to 3, and this is the output the reader may be interested in, right? And then if we want to go 2 to 6, 8, then we find 2 and 8, and this is something the reader or the driver may be interested in. So that's we want to have this one to provide it, but this also have some problem here, and we will explain later. And this is the adjacency matrix, which is that we according to this road-based partitions, then we can have this adjacency matrix like here, which means we here that we, for example, region 1, this one can go from region 1 to region 1. So we have put a connection here, and also region 1 is connected to 2, 4, 6. So that's it's 2, 4, 6 is 1. So in this one to indicate that whether these two regions are connected or not. Yeah. So this is described the spatial correlations. Then the problem is like this, that we, for example, that we have a historical observations. And here we notice here we have highlighted here is historical sparse OD matrices. So why it's sparse? Because here we have only eight regions in total, right? So that we need to have a 8 by 8. So it's around 64 regions. But in reality, the regions can be much, the number of regions can be much larger than this one, and it's square. So it's very hard for at each time interval, they have some data which from one region to another region. So in this case, that for example, at time t, that's at time t, that's here, this is t, maybe they do not have data at this question simple areas or origin and destination pairs. So, but for some regions, for some pairs, they have some distributions. So in this case, that for each time interval, yes, for each time interval, that this matrix is sparse, and the sparseness is different, because from t to t minus 2 and t to minus 1, they may have different pairs, which is sparseness. So that the sparse is randomly distributed, and then we want to predict the future 4 OD matrices, which is that for our prediction, we need to have the distribution at all cells in this OD matrices. Then this is our target. Yes. So how can we do it? This is our problem formulation, that we are given a S of historical time intervals of sparse OD matrices, and we want to predict a total of H forecasting time intervals in front. Yes. So how can we do it? Then we have a framework which looks like this. That this is our input, which is mt minus s plus 1 to mt. Yes. And then what we can do is that, for example, because this all these matrices, they are sparse. So how we can do some factorizations, which means that we can using some dense two dense matrices to represent this sparse matrices. And next step maybe that we can use these dense matrices to do the forecasting, which we can do this to predict this future matrix for this dense matrices. And afterwards, we can do a recovery, which we can just do R by C to recover this M, which is the forecasting matrix. And this is the basic idea that we keep in your mind, that our assumption is that for this factorization, that we can, for this R and C, they can capture the embedding or the latent space of these matrices, which at each column and also at each row, they have their own embeddings, and these embeddings are meaningful. And then we hear that once our embeddings are meaningful at each column and each row, then here once we do the forecasting, then they still each row and each column and each row, they are meaningful. And then we can do the recover back to this M. So this it's also like the inverse operation of this factorizations, so that it's still meaningful, so that we can get these predictions. So this is our basic idea for this one. But what can we do better for this factorizations? Then can we do something which is better than just to do this matrix factorizations, like in the mathematics, just to do randomly learn two matrix, small matrix, and to learn this sparse matrix. So here that we think about this, we slice each row or like this into n a total number of n slices, which means that for example, this n is the whole number of the destinations, right? So for each destination, we slice them out like this, and then for each row, for each column here, actually it's the number of the origins. So we can see that if we slice them, each row slice them together out, and then we can have this for this, for example, for this blue slice, right? It still have the column, number column is still n prime, which is number of the regions. So then we can do, for example, can we do it using a, can we consider about this graph connections, which is the adjacency matrix about these regions. So that we can apply this graph convolution here again. Then we can use this adjacency matrix of W prime and with this region, and then we can do a graph filtering or graph convolution. Then to do on this one, and then we can do a pooling, which means that we're pooling on this node on these regions, and so that we can condense or we can compress these dimensions for the features. And afterwards, we can get a total of n k feature maps, and then the condensed the dimension we set is beta prime. So here that we can see the input here for the k is the input feature dimension, and output we can set a same number of the feature maps, which the number set or the number filter is set here is k. So that this k is the same with k, but they are different. Here is a k for the number of the graph convolution filters, and this beta prime that is the desired dimension that we want to condense this one. So after that, we can get this dense feature map, which is like the R, which is the dimension here is this one is already, this destination is still n, and this we can compress this origin part with beta prime, and the feature space is still k. Yeah. So this is what we can do on this condense this original side, and then we can also do the same for this destination side. Yeah. And once we do this forecasting, yes, and then we can still consider about this temporal dynamics that we can use this GRU, which is very popularly used, and also for the spatial correlations, because when we do forecasting for this R here, so for this R here that we still have here for the destination side, it still have some spatial correlations, right? So when you do the forecasting, you still can think about, you can still consider about this spatial correlations. So here that we can do a forecasting, which is like this. We consider about spatial and spatial correlations and the temporal dynamics together in this forecasting modules that we propose. Yeah. And then for this part, that what finally we do just to do the recovery, and the recovery here it's nothing more special, because we just do the multiplication for the matrix for the R hat t plus j and at t plus j, and multiply by this c hat, which is at t time t plus j. So that this time interval that we multiply this R hat and the C hat, which is output for the matrices. And finally, we do the loss function, which is like this. And this too is the regularizations, which mean that they need to be as small as possible, because they cannot be too large. And also here that we do this this is the ground truth, and this is the this is the prediction, which is the M, and this is the ground truth. And then we have this omega here, and this omega here it's kind of indicative functions, which means that where this ground truth have values. If it has values, it is 1, and if not, it's 0. And then we take this Euclidean L2 norm as a loss function. So we need to minimize this loss function and then to learn our models. Yeah. So this is our basic idea, that how can we employ this spatial temporal correlations into forecasting and in this traffic data analysis. And this framework actually, some modules can be used in other applications, like the travel time estimation for the station level travel time travel data or something. Yeah. Okay. So next we come to this unsupervised path representations. Yes. So what is path? So let's first say what is path representations. So here is just a Google map that's this is from IKEA. That it's here that we just enter a IKEA, and then we want to go to my workplace, which is here. So that we can search on the Google, and then it will provide three routes. First is via this through this via this road, which is like the highlighted one, which is 30 minutes, and yeah, and this one which is going into E45 and it's 14 minutes, and then also there's another road which is going from here and it's 15 minutes. So it can provide different different passes routes, or and the travel time is also different. So the task here that we can do is we can do a path travel time estimation, at how much time this path is going to travel, and also that there's another task we are going to use or we are going to apply, that it can rank these passes from this one is the first, this is second, and this one is third. So these are something that we need to think about it. And so the path representation is that we are learning representations in a graph which can facilitate building various predictors. And this one is for, in this case, it's about the travel time estimation and also this path ranking and etc. Yes. So here that this is done some applications which the path representation can be learned. But what is the problem for path representation? So we need to come out to this, put out this graph representation first. So in graph representations, we have this node representation, which is here that we input a graph and take this graph into a node representation learner, and then we can get a graph node representations or graph representation. And for each node, the vector maybe it's dimension of D, right? So this is for the graph representation learning or node representation learning. And then we can have another one, which is that we still take the graph as input and input a graph representation learner, and then we get a vector for the graph. And this vector is it's the latent space to represent this whole graph, right? So this is the two different cases in graph. And because path is kind of like it's kind of special graph, right? It can be understood as like the subgraph in a graph. So what a path representation is that we take the path as representation, then we take the maybe from here for the node representations, we can take them for each node and to make this as the initial representation for the nodes. Then we put input this initial path representation into a path representation learner, such that we can learn a vector which can represent this path. Yeah, so this is our final goal, which can learn this one as a vector. So this vector can be used later words to do, for example, we want use this one to do this forecasting, path ranking, or something else. Yeah. So here that's for, let's take the travel time estimation example. So here that's we are given a neural network like this. So right, and then we can have some data we can do that to do this task, which is travel time estimation. Then we can collect a lot of passes. For example, 1, 2, 3, 4, and the travel time is 10 minutes. And then we have 1, 2, 6, 5, 6, 4, it's 30 minutes, and so on and so forth. We can have a total of large amount of passes and large labels accordingly. Yes, and then we come to a query path. For example, it's 4, 6, 5, 7, and then we want to know that, okay, what's the time should this path be, right? So this is kind of like the application for this travel time estimations. And the supervised way that for this path representation learning for the travel time is that, okay, we take all these passes as input, and then we input a path encoder, right? And then we get a path representations. And after that, we're using a predict head to predict that what's the travel time it is. For example, it's 10 minutes, it's 30 minutes, it's 50 minutes, and then it's 90 minutes. But in this case, if we want to train this model well, we need a large amount of data to train this model well, right? Label data. And then we come a query path, and then we input this path encoder, get the path representation, and then we come to this prediction head, and we get this 20 minutes. So supervised learning is a task-specific learning procedure, and it is difficult to directly use the task-specific representations or to other tasks. And it requires a large amount of label data in the training. Yeah. So here that's what we want to do is that we want to learn a generic. I think maybe I didn't use the pointer right. Okay, now so here that we want to learn a generic path representations for different downstream tasks, which, for example, is the path ranking that we talked before, and also the travel time prediction, and without specific labels, so that this path representation is more general, and this one can be used for different tasks. Yeah. So this is our motivation that why do we need this one? Then we don't need a huge amount of label data for these passes. So here that how to do it, and why to do it, because that's it's the label data is not always available, and also the labeling data is expensive and time consuming, and also we want to take advantage of a huge amount of unlabeled data, and we want to enhance the supervised learning using some pre-trained models, and we can also want to generalize to different downstream tasks. So this is the reason that why we need to think about this self-supervised or unsupervised path representation learning. So what is self-supervised learning? It means that we are given a set of paths P in a graph, and then the path representation learning is aimed to learn a path representation vector Pi, which dimension is d prime for each path Pi in this set, so that this Pi can be utilized to do a variety of downstream tasks. Yes, so this is our problem formulation, which we have input H is xi, and the dimension is z by d, and d is the dimension for the node, and z is the length of the path, and we want to come out a representation for this xi, and with Pi, and the dimension is d prime. Yeah. And the function or the model is called the phi is the learnable parameters for the path encoder or for the model. Yes. So how can we do it in a unsupervised or self-supervised way? So here is the example that we need to introduce a little bit. That's, for example, that we have this P1 as our input, which is the node is from 1, 2, 3, 4. Then we need to have some negative labels, negative passes, which is different from this part, so that we can use some constructive learning to learn these path representations. But for this path, actually negative paths, they have different difficulty levels. For example, here that for the P1 bar, this one we can see that it's going from 7, 5, and 6, and this one is the easiest. Why it's the easiest? Because this path, they have no common nodes with this input path, right? So this one should be the easy negative path. And then the difficulty level can be increased. For example, we can increase here to 1, 5, 6, 4. And why it's difficult? Because they have the common origin and destination point, which is the same with the P1, but only the intermediate nodes are different. So the difficulty level is different, it's increased. And then we come to this final one, which is the hardest negative path, which is going from 1, 2, 6, and 4. And we can see that they only have one node, which is 6, is different from this input path. So this is one of the hardest one, which is the negative path. So this is how we construct the negative path. So the negative path is that any node, any path which have at least one node is different, then we call it negative path. So how do we learn this? How do how do we learn this using this negative path? How do we learn these models? So first we consider about a global contrastive loss, which is that we input this path 1, 2, 3, 4 here, and then we have a negative path which we have V1, 1, 5, 6, and 4 here. So that's both of them can input take as input into the path encoder and get this path representations for this input for this PI for this path and also for this path, which is PJ bar, right? Then we have a path discriminator, which means that we need to distinguish that for this PI, which is the path representation, which we learned from this path encoder, it should have a similar similarity with this initial view, which is that we just take all the nodes here in this path and the node representation here, and we just aggregate them together and as the initial view for this path. Then this PI and the initial view, they should have some similarities, and this should be discriminator should be the positive one for this two. And for this PI and PJ bar, which means they come from different paths, right? So they should be different. So this path discriminator, they need to distinguish that okay, these two are different. This is negative. So this is a global contrastive loss that they need to distinguish. And then we also propose a local contrastive loss, which is like here that for this input path we have this path representation, and then for this path representation and for the initial node representations, we have a path node discriminator, which means that for this path representation, this should be have some similarity or be positive for the nodes which are coming from its own, then it should be the positive nodes or positive pairs. And then for this 5 and 6, which come from a different path, then it should be negative. So in this case, that this one we should using a path node discriminator to distinguish that whether it's positive or it's negative, and use this one to construct a local contrastive loss. Yes, and then we propose our framework, which is called path InfoMax, and this is we want to learn. We have a path encoder, we have path discriminator, and we have a path node discriminators. And this is our whole framework. We have this global loss and also the local loss. Yeah, and then we combine both the global and the local to train this model, which looks like this. And in this paper that we are using, we are taking the idea of the mutual information to do it. So that's why here it's the argmax, which we want to maximize the mutual information between this of this global and the local loss. Yes. Then once we have this pre-trained model, that how can we do to do the downstream tasks? So here this is our model, which like this. And once we have a training downstream task, which is travel time estimation, and we can have this data input path, right, and input as path encoder, and get the path representations. And for this representation, that we can using a prediction head to predict what's the travel time of them. And here that's the good thing that we can using this path encoder here. They are using the same path encoder, so that the weights which is trained in this unsupervised method, they can be used. They can be initialized in this one. And then we only train this prediction head to predict that what's the travel time it is. Then if we only train this model, then this model will be much smaller, right, than this model, so that we can using less training data to train these models. And then we want to get a query path which is 4, 6, 5, 7, and we can still input this path encoder, and we get this time for 20 minutes, for example. So this is something that we can try to use this apply this unsupervised path representations, and then we can do this one. Yeah. Yes. And then we have some conclusions and future works. First, that we will address that the data sparseness in the UTS for a rodent network. And then we can select, once we have this UTS, we can select the optimal path according to the user preference users risk preferences. But this part, due to time limitation, that I cannot give a detailed explanation on this part. And then we can do this forecasting, this UTS with spatial-temporal correlations. And then we can also learn the path representations in self-supervised or unsupervised manner. Yes. And then we also can have some more future works can do on this part, on this whole framework that we can consider about is continuous distribution models, which, for example, is Gaussian mixture models to replace our histograms, because histogram is something it's discrete. So maybe it cannot reflect a very fine granularity about this travel time distributions. Yes, and also that we can increase the interpretability of models. That's to how because for traffic data, if you need to provide some feedback to the users or to the end users, they may need something. Why I cannot take this road? So if it's better, we can increase some interpretabilities for the models. Yes, and also that we can also to explore some non-Euclidean manifold space, which means that because for a road network, it's like the graph, right? So the graph is not very good to describe in a Euclidean space. So what if that we can explore some using some non-Euclidean manifold space to continue this work? It's also a good try, I think. Yeah, and that's all for today's talk. And thanks for your time.
Yeah. So, is there any question? Thank you for Jilin. Nice talk. And for me, actually, I just have a little knowledge about the spatial and the temporal data and also the related methods. Can you just explain what's the data presentation for the spatial and temporal data? Just combine them in a same, maybe, I'm not sure, like the graph or something, just to represent the time and the spatial information in the data.
Okay, you mean the for the temporal and the spatial, they are not in like the graph space, like in other space, right? Is that right?
Yes. Yes, correct.
Okay, so here here I just give example that maybe it's easier to understand that what is the spatial correlation to model it as a graph. But actually for spatial data, that it can be other formats, like your cell phone. Actually, it's very easy to use your cell phone as a moving object, right? So when you are moving, that your signal, your GPS is emitting all you have all the records for the GPS. And these objects, they were moving. For example, this is one moving object in the red dot, and they can be moving freely in the space, right? So actually, this kind of like the when you move in the space and the object is not static, then it's kind of like the spatial things. And for spatial, and then when also that if you have two objects when they move together. And then you can also think about this spatial things. And then we can take this COVID-19 as an example. That I think that over the world they have some app in the very beginning that when two cell phones they are connected, they are very close using the Bluetooth to connect. And then if they stay there for a few, for 1 second or 2 seconds, then they can have some pairing. And if someone is infected with COVID-19, then the other one will be notified. And this is kind of like we take the spatial things in these scenarios. And for this temporal stuff, it's mean that it's kind of like here that because that the data is changing over time, so it's different from time to time. For example, now that you are spinning 1 meter per hour, 1 meter per second, and maybe you can increase next few seconds. So this means that your status is not static, so that it will change with the time. So it's kind of like the temporal dynamics. And then what you need to do is that you need to consider what's the relationship between this spatial and this temporal stuff, so that they can better combine together. So that's what we need to think about this spatial temporal correlations. Yeah.
Okay. Yeah, thank you. So first, for my previous knowledge for the temporal data, we just maybe some sequence yes. of time steps. So that yes. means just like the
time
stock. Yeah, time. Yeah, correct. Just something like that. So yes, I think your data presentation is fundamentally different to this time series, right?
Yes, because actually our time interval here it can be larger and it also can be smaller, right? So for the stock, for the sequences, it can be like milliseconds, like at 1 point, right? Because they have some exchanges, or it can so it looks like continuously. But in our case, that for the traffic, the traffic condition, they want to change too much with 1 minute or 2 minutes. So that may also that about data. So that we split the data, the time interval a little larger, which means that here we take 15 minutes, and maybe it can also be shortened to be 5 minutes or something. So it's still kind of like the time series, but the temporal granularity is different. Yeah.
Okay. Yeah. Thank you. So is there any other questions from our audience? You just can turn on your audio and just speak out, ask the questions. But I cannot read the question from the QA. Okay, yes, thank you. Thank you for Jilin. Nice talk. Thank you.
Yeah, thank you for your time. Yeah.